So in this section, what we're going to do is take a look at some applications that involve exponential functions. And so I'm going to start off with a couple of situations. There's actually many, and then within the situation, we'll talk about why this function behaves, or why this situation behaves the way it does, and then we can see other applications and just build from there. So the first situation, we're going to deal with the rate of change of my money in a bank account is directly proportional to the money I currently have in my bank account. So there's some language in here that we have used before. Rate of change, if you recall, right, that's basically a fancy way of saying slope. So the rate of change of my money, all right, so let's just say A is the amount of my money, right, so the change in my amount over a change in time, right, is directly proportional to, so that means it's a multiplication, so there's some K, it's directly proportional to the money I currently have. So the change in my amount, right, so this basically this slope is directly proportional to, so it's a multiplication of some constant times how much I have in my account. So that is what that situation represents, and that's actually how money behaves. The more money that I have, right, the change in my account is a percentage of what I had, right? So that's your percent interest rate that you're basically making. So if I have more money, multiply it by that percent, the change in money becomes more, right? And so classic situation. Can we sketch a possible graph of the situation? The answer is yes. I'm going to start, let's just say we start with $1 in our bank account. And so if I start with $1, right, so let's let that be the time and this be the amount that's in my bank account, then, you know, after, let's say, 1 year, when I have a certain percentage of $1, the amount of change, the amount that's going to be in my account is going to be $1, right, plus a little bit more. So maybe $1.02, right? And then the next year, right, that $2, that $1.10 multiplied by the same percent is now going to become like $2.30, right? And as we keep going year by year by year, what's going to eventually happen is at each location, right, the slope, right, of the line at each location is steadily going to get higher and higher and higher and higher. All right, so the rate of change is going to increase as the amount of my money increases. And so what we basically have built there, right, is what we know to be exponential growth. And it does turn out, it's beyond the scope of this course, but when you guys take a calculus class and you solve this, what you end up with is a function that is, I probably shouldn't have used A, but it's going to be, how about, well, I'll just call it A of t, right? So the amount in my account is the e to the kt, and then let me just call that A sub 0. So A sub 0 is the initial amount that I have in my account. K is that percentage growth rate that we have, right? So K is a percent growth, and the A0 is my initial amount. In this case, it was $1. And so, again, the math going from this directly proportional statement where I'm directly relating my rate of change, which we call the difference quotient, the average rate of change, and we've talked about directly proportionality being a multiplication. When you solve that, you end up with that. But hopefully that makes sense because of what I talked about in terms of as we go year by year by year, the amount of my account keeps growing higher and higher and higher. So the slope gets steeper and steeper as we go along. So it's a classic exponential growth curve. All right. So there's one situation that's money, right? But it turns out that populations also grow this way. The population of a city or of a county or of a state, right? The rate of growth is some percentage of what's there. The larger the population, the larger I expect my rate of growth. The smaller the population, the smaller the rate of growth. Again, we're all adults here. That just means less chances for reproduction if there's less people. If there's more people, that means there's more chances of reproduction. In today's world with COVID, right, it turns out that virus viruses, spreads of diseases also behave somewhat exponentially, because the rate of change, right, the rate of growth of the virus, right, is directly proportional to how many people have the virus. So if more people are infected, right, that's going to happen. And again, if we let T be the number of people, right, if there's only one person infected, then maybe that person infects 2 people. And then those 2 people go out and they, infect 4 people. And then those people go and turn and do 8 people. So before you know it, right, what we have is that nice exponential curve again. So money, population dynamics, spreads of diseases, et cetera, even some supply situations, when you guys look into your economics courses, behave as an exponential growth curve, right? So, and the reason that's happening is because mathematically, the rate of growth is directly proportional to what I currently have at any moment in time. So that's what it creates that, and I'll leave it to your calculus instructors to actually prove that to you. I'm just kind of finger waving and like abracadabra, boom, hope we understand. But that is a function we've studied, and that's a function that we can use to mathematically model situations. The second situation is slightly different. What's happening in this situation is, again, we have our rate of change of the amount of a radioactive substance is directly related to how much substance I have. So let me go ahead and keep using that A. So we're talking about the rate of change of my substance, right? So again, that's my average rate of change is equal to, right? It's directly related to, so that's a proportion, the amount that I have. But in this case, since we, so the amount of substance is what's going to happen over time is the substance is going to start decreasing in amount. So K, right, is still somewhat of a percentage rate, but in this case, K will be negative. Up here, K was positive because it was growth. And so if we started off, right, with 100 grams of something, right, I would expect that, right? So after the first year, maybe there's only half of it left, right? So it's got a 1-year half-life. And so after another year, it's at 25. And after another year, it's at 12.5. So if we go through that, what we end up with is our classic exponential decay. Okay, so that's our exponential decay model. And in this case, it's been shifted up or shifted over, because we usually have the intercept over here at 0, 1, like I did for that example. But kind of hard to explain it when we start. We only start with 1 gram of the substance, but I have the same idea. All right, so that's a classic situation. We have exponential decay, and again, if we mathematically solve this, right, the amount of my substance that I have is whatever my initial amount was, e to the kt. In this case, k is less than 0 to get the decay part going on right there. All right, and again, that'll become clearer in a calculus class when you actually learn how to solve rate of change questions, derivative questions. But for now, hopefully, just with what we know, we have talked about rate of change, right? So it's a slope, right? It's a difference quotient. We have talked about being directly related to something, so it's some constant times something, and in this case, it's the amount that I currently have at any moment. All right? So that is basically the situations we're going to be dealing with. Now we're going to be dealing with exponential growth models, and we're going to be dealing with exponential decay models, and they both pretty much have the same function. The only difference being is that up here for a growth model, that k value is positive, and for a decay model, that k value is negative. And usually, like I said, they're a percentage. Money-wise, it's my percent interest that I earn. Radioactive decay, it's the percentage left after a certain amount of time, right? Usually we call that a half-life when we get there, right? And we'll actually study that in a moment, right? So there's kind of your groundwork and your general idea of what's happening and why it's happening. Now what we're going to do is get to work and dive into some examples. See you guys in some videos soon.